VLSos here. This is a video lesson on limits with a piecewise function. I'm going to graph a piecewise function to work with, and then we're going to ask many limit questions associated with it. This piecewise will have a value at 0 of 5. At 2, it will have a value of 3. At -2, a value of 3, and the piece that connects those may be parabolic, but is curved like this. After 2, it's straight down. At -2, we have an open dot at 2, and then the values before -2 have a curve like this. Let's call this the g function. The first limits that we're going to ask are infinite, the end behavior. The limit as x approaches -infinity of g, and the limit as x approaches +infinity of g. These are examples of infinite limits, which tell us about the end behavior of the function g. And they're infinite limits because their approach statement below the limit symbol includes infinity, -infinity and +infinity. So how do we answer these questions? Well, we're working with a graph, so we have to assume that the graph is a representation of g and may not be precise. But we're going to do the best we can in reading what is intended by these arrows. The graph continues in that direction. So as x increases or goes to infinity, I would imagine what this graph would look like if I was able to see it continue. And it looks like this was drawn as a straight linear piece to suggest that it keeps going down as a straight line. And it would go down forever, so as x approaches infinity, it's going to go to -infinity. The values of the function, the y values, are heading towards -infinity. What about on the other end? If I was able to read the graph and follow this trend, it looks like the values of the function are going down, but it looks like the intention of the drawing was to suggest that they are not going down in a linear fashion, they're leveling off. And it appears that maybe the values will never go under the horizontal axis. So it looks like the graph is drawn with the intention of the horizontal axis being a horizontal asymptote. So they'll get lower and lower and lower, but never get to or cross the asymptote at 0. Now again, we don't have any way of proving those limits, but we have to make our best guess dependent on what the graph was intended to look like. The next limits are going to be one-sided. The limit as x approaches -2 from the left of g. Notice that there are two uses in this notation of the negative sign. One to suggest that we're talking about -2, this location in the domain. And the other negative, superscripted on the other side of the 2, is the notation for from the left, or from the negative direction. So we want to imagine that we're approaching -2 in the domain, but we're thinking of coming from the left of -2. That's a one-sided limit, and we'll answer in just a moment. Let's compare it to the other side of -2. The limit as x approaches -2 from the right with a positive symbol superscripted with the 2 of g equals. Now let's determine those limits. If I am to the left of -2 and I'm imagining following that trend of the curvature of this function, where do I think I will be as a y value or height when I get to -2? I think I'm going to arrive at 2. It doesn't matter that there's an open dot there, it's where I think I'm going to be. So the limit as we approach negative 2 from the left is 2. If I'm to the right of negative 2 on the function, and I'm traveling down the function trend in the curvature, where do I think I'm going to be or end up when I get to negative 2 in the domain? I think I'm going to be at 3. It doesn't matter that there's a closed dot there. It's where I think I'm going to end up. Limit questions are different than value questions. I could ask, what is the value of the function at negative 2? And the answer is where the closed dot is, 3. But the limit question is different. Though these two are one-sided, couple more limits. The limit as x approaches negative 2, without a plus or minus symbol there, this is an absolute limit, not one-sided. And because the one-sided limits at negative 2 are different, meaning they are not equal, then the absolute limit at negative 2 does not exist. For there to be an absolute limit at a number, the one-sided limits have to be equal, and they're not. We could also ask, what is the limit as x approaches 2 of g? So we're switched to a different number in the domain. At 2, we have a value of the function 3. But the limit question is not the same as the value question. It does not matter that there is a closed dot here. What we care about is the two one-sided limits. Are they going to the same place? Well, from the left, as we approach 2, it appears that we will get to 3. And if we are approaching 2 from the right, it appears that we will get to the same value 3. So the absolute limit as x approaches 2 is 3. There is a feature of this graph that we can highlight. There's a break right here that there isn't at 2. This kind of break is called a discontinuity, which we're going to study in the future quite a bit. But it's worth saying that the function is not continuous at x equals negative 2. In drawing it, you'd have to lift up your pencil at negative 2 to continue drawing. It's not continuous because you have to lift your pencil, which is an informal justification of why it is not continuous. The formal reason why is because there is no absolute limit at negative 2. To compare that, we could say it is continuous at 2. We don't have to lift our pencil to draw the function at 2, but formally it is continuous at 2 because the value at 2 exists and is equal to 3. The limit as you approach 2 exists and is equal to 3, and the value at 2 is equal to the limit. This is the formal justification of why it is continuous at 2. More on continuity in another lesson.